Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory as a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends to the SwayamPrabha course titled Marine Renewable Energy Systems, Analysis, Design and Development, where primarily we are focusing on wave energy converter design. In the previous lectures we discussed about the parameters, both on frequency and time domain analysis methods of designing a novel wave energy converter. We illustrated this to an example of floating wave energy converter. Credits to Dr. Srinivasan at IIT Madras, where the research was fundamentally carried out and patented jointly with IIT Madras. So in the last lecture, we discussed about the parameters that govern the selection of the device geometry. In this lecture number 20, we are going to talk about the wave parameters which will affect and control the power capture. Friends, we already know that power matrix is a function of various parameters. To recollect this from the previous lectures, we can say primary parameter controls the power matrix could be the C state, that is the wave climate. It can be wave amplitude and period of a regular wave, or it can be significant wave height and zero crossing period of a group of regular waves, what we call as irregular waves or nonlinear waves or random waves. So, these two parameters dominantly control the power matrix as an input. However, to harness the maximum power, we must tune the device in such a manner that the dominant wave frequency should be aligned in the closer bandwidth of the fundamental frequency of the device. Now, one may ask me a question, the device is a free floating buoy, it has 6 degrees of freedom. So, we will align this with which fundamental frequency? Is it the lowest frequency or what degree of freedom we should align with? So, the buoys what we are talking about is having a free degree of motion in heave and pitch. Rest of them are not activated for a unidirectional wave which cannot be harnessed actually. So, we are talking about harnessing the energy, it is not the motion of the buoy. What is the difference between motion of the buoy and harnessing the energy? Let us see this. So, the motion response is with 6 degrees of freedom, as we all know, that is, for example, surge, sway, heave, these are displacements along x, along y and along z. Then rotation about x we say roll, rotation about y we say pitch and rotation about z we say yaw. So, 3 translational degrees of freedom and 3 rotational degrees of freedom. So, a buoy has got 6 degrees of freedom. Now, what we are talking about harnessing, which is different from the degrees of freedom, is that harness can happen only when you apply damping and control the response, in fact, and stop the response, okay, and damp the response. When you damp the response, that damping is the harness. Okay. So, we do not want to damp the surge and sway motion because there is a free body motion of the buoy. We do not want to harness the direction at all. We only enable recentering of the buoy by providing the tethers or the mooring lines, so that the mooring lines will act as a recentering element to bring the buoy, or the restoring element to bring the buoy to dynamic equilibrium position at any point of time during its operation. So, surge and sway are not considered to be a harnessed energy direction at all. Similarly, for a unidirectional wave, you will notice that roll, which is about x, cannot be a functional degree of freedom. Of course, for a body symmetry, we generally do not activate yaw, right. So, the rest which is available to us is only heave and pitch. However, if I look pitch as a differential heave, or I can always consider pitch and heave as interdependent degree of freedom, or what we call otherwise in dynamics as coupled motion, I can always harness heave by using an external damping device, what we call power takeoff mechanism, so that pitch can also be vice versa controlled by the same PTO. Therefore, in the previous derivations, we clearly saw that the 6th degree of equation of motion is converted equivalently to a single degree of freedom motion in heave, and we understood this how the equation of motion is solved in time in frequency domain to get an virtual PTO damping, then apply this to a time domain analysis in nonlinear time history and get the response of a system. Therefore, we are able to obtain the captured power by the device. Please understand, friends, we are not still reaching a stage of power delivery to the external system. So, we are talking about power captured by the device. Once the power is captured by the device, this power has to be transferred, okay, by as electrical energy or mechanical energy to a system, what we call as a generator, linear generator. So, this is the design of power takeoff system. We have still not come to that part at all. We are still working at how to maximize the power capturing phenomena for a chosen geometric design of a wave energy converter, right. So, in this perspective, let us say the power absorbed will be between the relative motion of the floats and the central buoy, correct? To recollect, let us say we have a central buoy, we have floats placed on all four directions. The central buoy is free to move in the heave degree of freedom, and the bean shaped buoys also move relatively with respect to central buoy. Why I say relatively? Because the central buoy and this bean shaped buoy are connected by an integrated arm, what we call as a connector arm, right, the racker arrangement. Therefore, the relative motion between the main floats and the central buoy with an assumed linear damping is what we are looking at this moment. So, now I am saying the power absorbed can be due to the relative motion between the central buoy and the bean shaped floats. Whatever may be the number, we already said in the previous set of lectures, we tried with an example of 4 floats. We also showed you the results of 6, 8 and 12 floats as multi-body dynamics. Okay? So, we take up an example of 4 floats, let us say, and continue with that. So, now I am going to impose a linear damping to the system. Now, the question comes, why I should impose a damping to the system? If you want to impose damping, then only can harness power. Why linear damping? Because we really do not know the non-linear terms contributing to this damping. That can be only obtained by experimental studies, which I am going to discuss in the further lectures. Therefore, now we are applying virtual linear damping to PTO, and we try to find out a different set of range of this PTO damping values to PTO and see at what damping value this gets the maximum power capture. We said that in the previous set of lectures, and we showed you the results from the time domain analysis. Okay. Now, we write down the control equation. We say that the power, the linear damped wave energy converter design will be now equal to the linear damping applied from the PTO, which is a function of or product of z dot of the float minus z dot of the central buoy. Z is the heave degree of freedom, okay, V square, right, and we always take up unidirectional power. We do not take a negative, there is something like negative power, right. So, we take an absolute value, mod value of this. So, this can be equal to now C radiation PTO, only the radiation damping, okay, of omega F minus omega C the whole square. This will be equal to this, we already showed that in the previous set of lectures, equation number 1 for the local lecture. Of course, when you look at the equation continuously from previous lectures, you should number them appropriately, okay. So, this is equation number 1 for this lecture. So, we say that the power absorbed by the linear damping applied to wave energy converter is a function of the damping on a PTO with its product with the heave velocity, which is relative between the motion of the floats and the central buoy. Okay. So, nevertheless, we write down that let us say in this figure we make a small change. Please note down this, the PTO is linear initially, later on it became radiation. Okay. So, we are only harnessing the radiation damping, which is a function of square of relative frequency difference between the float and the central buoy. Friends, one way of getting the maximum power is putting the peak frequency of the wave input to the fundamental frequency of the system. Now, the system has got relative motion. There is no single fundamental frequency of the system. Floats have a different fundamental frequency. Central buoy has a different fundamental frequency. So, I am looking for the relative difference between these two. I am harnessing that with the peak frequency of the wave. That is how I can get the maximum power. Okay? Therefore, in this equation 1, we can say that C R PTO is the rotational damping matrix. Why I am saying rotational damping matrix? Heave is the motion which is happening in the buoy and the float's differential. But I am applying a PTO as a torque meter to stop this motion. So, now the translatory is converted to rotary. Okay? The translatory motion, the translation, that is the heave, is converted to rotary motion, that is the pitch, or you can say even torque. So, you know friends, in mechanical engineering you are aware, torque meter is a very simple device where if you want to measure a torque of a rotating device, let us say I have a shaft, I want to rotate this shaft by some torque moment of certain Newton meter. I want to measure this torque. How do I do it? I provide a brake to this, keep on rotating, this brake will measure the torque and give me the value. Similar mechanism here. I am having the heave motion of the central buoy. The heave motion is created in the central buoy because of rotary motion caused by the floats. I want to harness this difference. So, I want to measure this torque. I am applying radiative torque or rotary motion to the central PTO. Okay. So, now the radiational or the rotary motion is the harness energy now, which is expressed in Newton meter second per radians, and of course Z dot F minus Z dot C is the relative heave motion. I think nevertheless you can understand this. Relative heave motion between the floats and the buoy. Friends, you will notice in the equation this term is already squared. Okay? So, there is no directional effect of this specific concept, is relative motion in absolute terms. Okay? What we call as net heave. Okay? When you talk about frequency, we say omega F minus omega C, again this is squared, this is relative angular velocity. Okay? Because we are talking about CRPTO, therefore I am going to use relative angular velocity. Now we move it to pitch motion. So, what I am actually doing here friends, I am harnessing, I am converting, I am transforming heave motion relative to pitch motion relative, and this is done as an external applied damping force which we call as CRPTO. Okay? Rotation damping matrix applied to a PTO which is virtual, is not measured yet. Okay? Measurement can happen only in the experimental side. Right. Having said this, initially in the equation we had linear PTO, you must have noticed that, okay, which is now transformed and expressed as rotational PTO. So, I have converted the linear motion to rotary motion now in terms of the PTO value applied to the damping. Okay? Now, we can write an equation for this. The linear PTO is given as the damping on the rotational PTO, which is actually a product of omega F minus omega C square divided by ZF dot minus ZZ dot square. So, there is a connection between the linear PTO and rotational PTO by equation 2. Okay. I want to now find the time average power, because now this is going to be on a specific bandwidth of frequency, right? Omega f and omega c has got specific bandwidth, right? I want to find the corresponding time average power per float. So, the corresponding time average per float. We are all working for one float, friends. So, the relative motion is between one float and the buoy, not all the 4 floats. Okay, you cannot multiply this with 4 floats because one will be compensating on the other. Be very careful about this. Okay, so it can be given as PA, which is given as 1 by T of 0 to T of P linear damping applied on vec of dt, equation 3. We call this as PLD vec bar. So, this is time average power per float. Okay. Now, we also said in the previous lecture that the time average power also depends on the absorption length, what we call later on as capture width ratio. So, let us say the absorption length given as LB, or let us say small lb, which is given as the LD vec divided by PRW or PIRW. Okay. So, now the absorption length will also contribute to the power capture. We call this equation number 4. Okay. Having said this, now I want to find the maximum absorption length, because maximum absorption length will be directly proportional to the power capture. So, let us say the theoretical maximum absorption length. I am looking at this in heave degree of freedom, is actually given by L by 2 pi. Now, the question is, what is L? This of course have a reference of Babarit 2015. Friends, the lectures what we disperse here, what we give here is a curtain raiser for your future research. So, please refer to all the original citations given in the lectures, read the original papers, understand the thorough modeling of the authors and grow your knowledge. Okay? So, I am not having time to explain all those studies conducted by various researchers on wave energy converter designs. Of course, I am citing them in my lectures. The list of reference also available in the SwayamPrabha website of this course. Please download those papers, read them thoroughly and understand. Okay? So, Babarit said the theoretical maximum absorption length in heave degree is equal to L by 2 pi. Okay? Now, I want to say what is this L in this case? I should say L is referred to as effective length, okay, in the heave degree. Now, if you want to compute this, this can be computed using something called equivalent area of a circle. Why circle? We are looking for a buoy. Buoy is circle in diameter. Therefore, equivalent area of circle we can say. So, L effective equivalently can be given as simply square root of 4 by pi. So, you will notice that this equation is similar to area of cross section of a circle. Okay. So, therefore, friends, AH is the maximum cross section area of the floats. Therefore, friends, you will notice that the maximum cross section area of the floats depends upon the effective length. Now, I can simply say L effective is actually approximated as the diameter of the float, correct? So, if you want to have a larger capture width or the power capture, you must have a larger float diameter. But the question is, we are looking at multi-body dynamics, therefore, there can be interference effects between the adjacent floats. Therefore, there is a trade-off between the diameter chosen for the design of the device and the number of floats placed on circumference. Okay? It is not always you try to work with the largest diameter. You have to have a trade-off between the diameter of the floats and the number of floats which you prefer in the design, because in multi-body dynamics you will notice that the interference effects play an important role in power harvesting. Okay? So, let us remember this in mind. Therefore, L effective, though it is as termed as diameter of the float, for harnessing the maximum power, do not always assume that I should have a float of a largest diameter. Okay? Then friends, now we are looking forward for the effect of the power capture and multi-body a number of floats. Let us say we try with 4, 6 and 8 floats. I have already shown the geometrical arrangement of these floats in the previous lecture. Please look at those figures. So, in general, I will have a central buoy, then we will have bean shaped floats 1, 2, 3, 4 or then 6 or then 8. Okay? So, the 3 configurations we are looking at now in our understanding. So, we are now looking for multi-body interactions between these floats. Why we are looking for multi-body interaction? Because the power harvest is a function of the relative frequency between the float and the central buoy, is it not? Now, when there are adjacent floats placed very close to each other, the interference effect of this float on the other, which is now transferred as a net effect to the central buoy, can become a question mark. Okay? Therefore, I must look at the interference effects of these floats when they are larger in number on the periphery. Therefore, float layout becomes an important element of study in the design, apart from the geometric shape of the floats. We already saw 5 configuration of floats: rectangular, rectangular closed ends, then bean shape closed ends and the torus. We already saw them in the previous lectures. So, geometry of the float is one aspect of the design. The second aspect is number of floats on the periphery of the central buoy. Okay? So, one can use this. Let us see how do we lay them here. Look at this figure. These are the configurations what we are now attempting to study. Let us say I have got 4 floats arrangement. This is one what we have. Then we have 6 floats arrangement. This is what we look at. Then we have 8 float arrangements what we look at. Okay. So, now we are looking for a different configuration of the float numbers. Let us say look at 4 float arrangement. We look for F4, we say A3. A3 is this configuration. Okay. If I say F6, B4, it is this configuration. If I say F5, B4, it is this configuration and so on. So if I say F8, C5, I am looking for this configuration and so on. So I am looking at a specific float and considering the relative motion of that float with respect to the central buoy in my study. Okay, having said this, now let us see what are the effects of hydrodynamic coefficients on this design layout. Effects of hydrodynamic coefficients on the layout of the buoys. Friends, if you recollect the lectures what we had in the previous set, we said that frequency dependent hydrodynamic coefficients are estimated using the boundary element method, and we already shown you the building blocks of this particular methodology. Then this was transferred to the time domain model and we analyze floating wave energy converter, which call as buoyant floating wave energy converter, and we showed you the configuration of these and the results as well. Okay. Now let us see the effect of the excitation force, which is frequency dependent for different layouts. So we already shown you the layouts. Let us look at the results. These are already published in the journal Energy. Please have the complete paper with you to understand the results thoroughly, but I am showing only the samples of them. So I have taken 4 float arrangement, 6 float arrangement and 8 float arrangement. We have now considered initial wave angle as 0 degrees. Okay. So there is a layout comparison given for A1, A2, A3 and so on for all the floats, okay, for all configurations of 4, 6 and 8, and you will notice that the excitation force reduces, okay, reduces with the reduction of float size. So we understand that it is a function of capture width ratio. Okay, that is very important to know. So the number of floats can help you to harness higher energy, no doubt, but since the periphery of the diameter around the CB is fixed, reduction in float size can affect the excitation force. So there is a trade-off between these two which we must understand. That is the first point we noticed. Okay. The second point we noticed is the frequency band where the floats are active in harnessing energy is a broadband. You can see that, okay, it has got larger bandwidth, right, larger, okay, larger bandwidth, it is a broadband, and this frequency band of interaction increases, that is very important, increases with the increase in the float number. Now friends, there is a very interesting compromise we have. On one hand we say when you increase the number of floats, the effective width gets reduced, it affects power or exciting force. On the other hand, we also notice that the frequency band of interaction increases with the number of floats in number. So one has got to decide a cutoff between how many number of floats should I have and what should be the minimum dimension of the float, so that I will get the minimum power actually from a given float. Okay, that is how we decide how we fix this. Okay. We will also comment saying that with the large number of floats placed around the central buoy, we can say that the net excitation force increases, okay, is improved. So this is one clue which I leave it for your understanding, that between these two trade-offs, what is better? And we all know that this excitation force is directly proportional to the power, or we can say absorbed power, to be very specific. In fact, the absorbed power is proportional to square of the exciting force. Okay? So, it is very influencing parameter. Having said this, therefore, we notice that the float with 8 configuration from our study, the float with 8 configuration is the maximum or has the maximum absorbed power. Though for 8 configuration layout, the capture ratio may be reduced effectively, but however, since it is square to the number of floats or excitation force, therefore, we say that 8 configuration has been seen from the studies, from the example study, it gives me the maximum power. What are the other factors which control this? Let us learn that also. The other factors control them are the frequency dependent, radiation damping, because we have used virtual PTO and we said virtual PTO is function of frequency. So, the frequency dependent radiation damping and the added mass influence. Okay. So, these are other parameters which is to be also considered in the trade-off when you discuss about the number of floats what you want to add to the system. Okay. Having said this, we can now consider one important statement saying that the radiation resistance, in fact the correct word what I should use is damping, because resistance is what we say as damping. Okay. The radiation resistance and the added mass, the trade-off factors are not dependent on one, the orientation of the floats of the wreck, 2, position, where are you placing the wreck from the coast, 3, incident wave angle. Okay. Whereas the excitation force is a function of them. So, this is very careful statement, friends. The excitation force is a function of them, which I can say it's a function of ultimately the float geometry. Okay. So now we have got two deciding set of parameters. One is the float geometry, two is the arrangement of floats. That is the number of floats, equivalent diameter, effective capture width length or absorption length, etc. Out of these two, which will be the most designing parameter to harness the maximum absorbed power? Okay, that is a very interesting question. Now, it cannot be answered because in simple reason we cannot compare apple and oranges. Both are equally important, right? So, we cannot simply say amongst these two parameters which is most governing, right? We say they are both important, but there is a trade off between these two. So, a designer has to understand this very carefully, and then he has to select the geometry of the float and the number of floats. Okay. Then what should be the parameter to maximize in the design? The parameter which is to be optimized in this trade off is not the absorbed power, it is the radiation resistance. Okay. Or I should say radiation damping. That is the factor which you have got to optimize. Okay friends, that is very important to learn and understand this. Now, we also understood that there is a strong coupling to be very precise. I should say interference instead of saying coupling, interference between the floats. Okay. This should be also understood as a parameter. We call this parameter, or we identify this parameter in the design as CRPQ. Okay, which we call the strength parameter. So now I want to find out the optimum damping ratio, right? That is what I am interested in. So I am looking for the optimum damping ratio for PTU, right? So C optimum is given as square root of CR omega square plus omega times of mass plus added mass function of frequency minus rho g AW by omega and to this square. Equation number 6. In this equation, we can say M is the dry mass and AW is the mean water plane area. Which will govern the capture width ratio, we can say, of the floats. AM CR, or actually frequency dependent added mass and radiation damping coefficient. Okay, of the floats. which you must obtain from aqua boundary element method solver. Then we also saw that added mass is also geometry dependent. So, let us see, we have the results with us for this. So, we have the results of, let us say, let us add this particular statement for our understanding. Add further, added mass is also function of geometry of the floats. It also influences the heave motion of the float, which we call as APQ, the influential coefficient. Therefore, friends, the added inertia arising from the added mass due to the acceleration of fluid particles in the vicinity of the floats will be higher and will be present across a wide frequency band. Okay, friends. So, this is responsible to make the device effective for a wider band of frequency of operation. So, one has got to choose very carefully about the geometry of the floats. Now, one can also neglect the effect of body to body interaction while computing the frequency dependent hydrodynamic coefficients. Then one can compute the frequency dependent radiation damping. So, the figure now shows here the frequency dependent radiation damping already published in the journal, frequency dependent radiation damping for different configurations of 4, 6 and 8 floats. Okay. You will notice that the 8 float configuration, though all of them operate for a wider frequency band, but the interaction of 8 floats is much higher in terms of PTO damping or radiation damping compared to the 4 and 6 floats. Okay. Now, friends, if we move on to finding out the average absorbed power, which is our focus for this lecture today. The average absorbed power of all layouts for isolated floats and integrated floats need to be studied to compare them, right? And I want to find the interaction effect of this. So, the interaction factor could be calculated, which is actually frequency dependent, and this should be an element present which we call as a Q factor. Now, this is computed for the specific case what we are explaining in this specific example, where the Q factor is the interference factor, which is given by a simple expression Pn by n star Pi. Equation number 7, where Pn or Pi is actually given by 1 by T 0 to T, the linear damping of the vector, which I already have in equation 2 of dt, which is also equal to half omega square the PTO damping of z bar omega square. Equation number 8. Okay. Where n is the number of floats. So, where n is the number of floats. In our study, in our example, we have said the floats taken are 4, 6 and 8. Okay. Omega, of course, is the wave frequency, and z bar omega is the complex amplitude in heave. Okay, same as this equation what we showed earlier. Pi represents the isolated average power. So, look at this equation, friends. I am comparing the total power absorbed by the entire system of n floats with number of floats multiplied by the power absorbed by each float. So, we call this ratio as interference factor. Okay. So, for our understanding, let us write down this also. Pn is the total average absorbed power. For the given float layout, considering all the floats, whereas Pi consider only for isolated power, right. So, friends, for our understanding, if Q, the interference effect, is less than 1, that is, the total power absorbed by all the floats together is lesser than the individual power absorbed by the float multiplied by the number of floats. Okay. We call this as shadowing effect in the literature. Okay. This shadowing effect depends on the layout and the number of floats. Okay. So, friends, let us come to the summary of this lecture. In this lecture, we understood what are all the factors which influences the average absorbed power of the design of wave energy converter. We studied something about interference effect. We learned about the effective length of the float. We understood that there is a trade-off between the number of floats considered for the analysis, the geometry of the floats, etc. But the optimization happens not with the power, but with the radiation damping of the PTU. Okay. Thank you, friends. Stay continued. We will discuss further more points of the design aspects in the continued lectures. Thank you very much. Namaste.